What's a bit strange in this talk is that where you're seated has an effect on the demo. So if these are orchestra sections, if you'd like to play a different instrument, then you can move around and pick a different place. So strings 1 is violins, strings 2 is cello and contrabass, woodwinds is all sorts of flutes, and brass is all the horns and trumpets and tubas and that sort of stuff. Yeah, we don't have much strings 2 right now. You're a double point of failure. It would help if you sit in a bit of an empty section, because then it's more spread out, right? I guess. And these are several. Is it time to go? Yep. All right, then we'll start off slowly. I realize it's the end of the day, and I'm the only thing standing between you and drinks. So we're going to try and keep it not too long so you can enjoy your afternoon. With this talk, it's a bit strange. Where you're seated has an effect on the demo. If the demo works, we require internet. So please pray for internet. Let's see, who am I? I'm Berwout Robles. I'm here to tell you about HTTP 3 and the new features that we can all use in HTTP 3. I work for Open Value. You might have seen my boss, Bert-Jan, this morning. And I currently work for Alliander, and I work on a part called congestion management, which is the flows of electricity in our grid, and they actually supply the power here as well, I'm pretty sure. And HTTP 3 is about network congestion as well, just a different type. So it's like right up my alley. If you want to reach me, you can hang out on Twitter or LinkedIn or email me. Anything is fine. Or just talk to me. All right, the topics for today. We're going to start out a little bit back to school, because most Java developers haven't seen HTTP in a long while. So we're going to go over the HTTPs that we know quite fast. Then we're going to talk about the new HTTP, HTTP 3, which came out this June. Then finally, we're going to talk a little bit about what that means for reactive streams and how we do reactive streaming inside Java. And then we're going to end up, hopefully, with a working demo. We still need the internet to work. The HTTPS we know, because everybody uses HTTPS, right? Starts out with HTTP 1. 1.1, it's like 1993. It's like 1 year after I was born. Very simple. We have a method. You call it on a URI, a resource indicator, which points to which resource you're trying to get. And it has a version. You have a few headers that are metadata. Then you have a forced enter, and then optional content. And it's a request-response model. You request something from a server, and you get a response back. And you cannot send something from a server without actually requesting it, which is quite nice. Then the response returns with what's HTTP version you're speaking, a status code, some headers back, another white space, and some content. Right? Everybody familiar with that? Who sees this for the first time? I'm wondering. OK, nice. Not that it's bad to see this for the first time, by the way, just to get an indication of where you all are at. So the stack we use, you might have seen the OSI 7-layer model, had it somewhere in school. Stack we use HTTP on top of TLS, which is the transport security layer. And then it goes down to TCP. And what you might notice over here is that these blocks are not really the same size. So sometimes in HTTP, record gets split into multiple TLS records, which gets split into multiple TCP records. Can lead to problems sometimes, because when you receive a TCP packet, and it's part of a TLS record that you're trying to decrypt, but you don't have the second part yet, you can actually not decrypt the record. So you're stuck with that TLS half record inside your buffer until you receive the whole part, and then you can start decrypting. So the difference in sizes there sometimes leads to problems, especially when you lose packets. So let's say you lose the second part of this TLS record, you get stuck with this first part in your buffer and you don't know what to do with it, right? HTTP 1.1 had a big problem, which was head-of-line blocking. We used to deal with these HTTP requests usually on an individual thread. So when you made a request, the web server would open a thread for you, and your request would get handled on that thread. And to prevent overloading these web servers, we would limit the amount of connections that the browser was allowed to make, or a client was allowed to make to a server. So you would usually limit this. Typically, it used to be 6. We did invent Keep Alive, so we could reuse the same TCP connection for multiple requests in a row. Typically, you would see it that you would fetch an index.html. It would point to a bunch of other resources you would need to go get, and then you would wait until the TCP streams were free, until you can do this unhappy request that is now unable to be processed until the other responses return. And there's also a bit of queuing difficulty, because it's like at the supermarket where you have 6 different lines, and you're trying to pick which line to go into, and then it turns out that cashier has a problem, right? And you're stuck there waiting. That's what could happen to this poor packet over here. We did some sort of hacks to prevent this from happening. So what we would do is we would put a bunch of CSS that you see here inside our index.html. So you would use one less request, but obviously it was much less readable. Something other we would do is you can only open 6 connections to one domain. So if you host your app across multiple domains and then put 6 files on each domain, then you could still parallelize the whole thing and pull it in at once. But it was a lot of complexity to deal with just because we couldn't open more TCP connections, right? Kind of annoying. We also dealt with this. This is TCP slow start, basically as a matter of congestion control, so that we don't overload the network. TCP tries with 1 packet at first, and then if it returns correctly, it tries with 2, and then with 4. We call this our congestion window, how many packets are being sent at the same time. And then at some point, there's going to be a packet missing because there is congestion. At that point, we stop increasing the congestion window, and we know this is the maximum limit the TCP line can take, right? But every individual TCP connection that you start, for every different request you make, still has to go through this slow start procedure unless we keep it alive, which we can do in some cases, but not in all cases. So you're dealing with this slow start on the same resource. So you know that this resource has a congestion window of X, for instance, but you can't use that because you're dealing with TCP, and it doesn't know. Then we got a huge improvement in HTTP 2, where we went to do multiplexing on the HTTP level. So where you saw the original message from the GET request, we would split that into multiple packets and then transfer it over a single TCP stream. So now we no longer have to open multiple TCP connections, but it's just one stream. And we instead multiplex the HTTP requests. Both request and response go over the same connection, and then it just patches it back together. So you see here, these packets are split up, and then we patch it back together on that side. Note that this doesn't solve the half TLS record problem, because the TCP doesn't know what's inside of here. So one annoying problem you can run into is one of these packets gets lost. Let's say orange number 1. Theoretically, that would be fine for the yellow and the green streams here, because they can still start decrypting and start processing whatever comes in, because they didn't lose any packets. But because this splitting is happening on HTTP level and TCP doesn't know about it, TCP just thinks, oh, a message got lost. I have to wait until this is retransmitted. So it holds up all of these requests as well. So previously, we had a problem where the 7th TCP connection would cause a problem. Now we have a problem where we have individual streams, except they're not individual because they run over the same TCP connection. So when one packet gets lost, the rest is still stuck waiting. So we have a new head-of-line blocking problem. In summary, we have head-of-line blocking. It's what we call both the first problem and the second problem. It's kind of tough to deal with because the TCP protocol doesn't know much about the actual data it's sending. We also have to deal with this TCP slow start every time we open a connection. HTTP2 has to start less connections, but the problem is still there, right? You might know the server beforehand. You might know it can take a certain amount of data, but you still have to start slowly. TLS is optional for both these protocols. I say optional, but browsers enforce it for HTTP2. So if you want to use HTTP2 and you want to navigate anywhere, you actually have to use TLS. But if you're in your own cluster, you could talk HTTP2 to one another without starting a TLS connection. And both of these run over TCP. All right. Everyone still here with a nice. HTTP3. Fundamentally different from HTTP 1 and 2 because the entire stack changed. For HTTP 3, we rely on UDP, and you might see that this TLS block has become a transport protocol we call QUIC, and it also combines itself with TLS. So there's no option to start a QUIC stream without TLS. And then the HTTP protocol still lives on top of that, and remarkably, besides being in binary, because HTTP2 also introduced a binary translation of the text to a binary stream, which we can obviously encrypt. Sorry, not encrypt, compress. So they introduced compression. So it's binary, but pretty much if you translate it back from binary to text, it's still the same protocol, still the same text protocol you're used to, except it now runs on a different stack. And what does this stack give us? Well, a difference between TCP and UDP is that UDP doesn't really care about congestion control, and it doesn't really care about acknowledging the fact that a message came back. So the difference here is that you just start sending, and you hope that they receive, except QUIC kind of takes care of that. So QUIC takes care of acknowledging the fact that a packet came back. And we'll see that in a second. All right. TLS inside QUIC also allows this neat little trick that we're going to see on the next slide. Be careful, the next slide is going to be a little bit complicated. I would say start on the top left, and then we slowly move across the top, and then we go to the bottom. Yeah? All right. So a QUIC connection has a little advantage where with a regular HTTP 1.1 or HTTP 2 connection, the protocol doesn't know about the encryption, right? So first you have to say, oh, I want to open a TCP stream. And then you have to start the TLS handshake, basically the exchanging of keys and picking which cipher you're going to use, and then exchanging your secrets. And then you can start your data transfer. But you have to go back and forth quite a bit, right? And the further away you are, the more this matters. Like if I'm hosting in Australia and I'm trying to access it from here, every round trip is going to cost me 300 milliseconds, right? It's going to be pretty painful. Then we have the option of TLS 1.3, which came out a while ago and can already be used. The main difference there is that the TLS handshake is one shorter, and it does this like over time, we've kind of converged on what algorithms we're going to use most for encryption. So when the client says hello to the server, it already suggests a protocol that it wants to use, and it already sends it keys in that protocol. And then if the server accepts it, all you need is one round trip instead of two. So here, usually, on the top left, you would still decide, oh, which one are we going to use first, and then send your secrets? Whereas in the second one, the client suggests, oh, this one is the one I want to use, and then it just hopes that the server also supports that. So if that goes wrong, you obviously do need an extra handshake still. And then for QUIC, because you don't have the separate TLS handshake, right? With UDP, you can just start sending. You eliminate an extra round trip because you can do the QUIC handshake, which includes the exchange of keys like TLS 1.3 does. So TLS 1.3 is the default inside QUIC. Then on the bottom, we have another neat little trick, which is that if you've visited a server before, then you probably know each other, and you've already talked to each other once. So in TLS 1.3, there's a new mechanism to restart sessions, where basically a client gets assigned a session ID, and they can reuse that session for the first request they send next time. And then the second request, or the response, the server will already send back new keys for the transmission to be safe again, because if someone steals your session key in the middle, they might be able to make requests on your behalf. So this way, only the first request is really vulnerable to that mistake. And there's one other caveat there, which is that repeated attacks, like if you repeat someone's request, you can actually, that is a valid request. So they say, when you do this, the 0 RTT QUIC variant in the bottom right, be very careful that it's not an action that actually does something. So it shouldn't be a mutating state action, right? It shouldn't be something that sends a bank transaction, because an attacker could repeat it if they're the man in the middle. All right. So QUIC streams look a little bit similar to the HTTP2 multiplexing that we had, except that each individual request gets its own QUIC stream, and you can kind of visualize this as a TCP stream on its own. So the congestion control is inside QUIC, and it's similar to TCP. The acknowledgement of package is inside QUIC, and it's also similar to TCP. They're also bidirectional, so both the request and the response go over the same QUIC stream. And what's really cool, HTTP2 already allowed you to open multiple requests, like more than 6. You could, but there's a limit. There's a limit of, you usually negotiate with the server about this limit, but usually it's around 250 streams that you can open. With QUIC streams, it's limitless, so unlimited power. There's also something that's very useful for cell phones, is that every QUIC connection has an individual connection ID, independent of which server you are connecting from or to. So you can resume a session with a web server from a different IP address altogether. So if you're in contact with the satellite over here, it drops out. You get a new connection, different IP address. You can start sending immediately on the same connection with your same TLS keys you already had. And the server will recognize it because it has a unique connection ID. So that's very nifty for cell phones when you're traveling and it spots a different cell phone tower, you know. Usually that would lead to connection loss. Here it could still lead to a lost packet, but you are resumed much quicker than you originally were. All right. Then about how do I actually go and use HTTP3? Because I want unlimited power, right? It's a bit hard right now. In Envoy, it's actually available for production use for downstream clients, so you can use it to serve your websites. The upstream, they're not really done with the congestion control part yet, so they don't recommend you using it for upstream connections. Nginx, it's experimental, and you have to compile yourself. It's a build it yourself and go ahead. Traffic, it's experimental, but it is built in. So you can actually set a flag that says use experimental true, like we do with the preview version in Java or something. And then you can just use the HTTP3 version. Netty support this experimental, and Apache isn't even on the planning. I listed web servers that I know and use. There are a fair amount of open source net web servers that do fully support HTTP3 already. They're just lesser known that I haven't encountered yet. So But a lot of it is still experimental. So be careful, I guess. Maybe don't use it in production yet. It was only released this June. And you might also think about, well, we have this nice round-trip production, which leads to a lot of latency that we now get when you connect to faraway places. Right? If you're in Amsterdam, it doesn't really matter that you go 6 millisecond extra round trip. But further away, it makes a lot of sense. We have this connection resumption with a connection ID. We have stream-specific acknowledgement of packets. So if we lose a packet, the rest of the stuff doesn't have to wait. We have TLS built in. Oh, there's one feature I forgot to mention, is that the messages are sized in a way that they are individually encrypted, which means that once you receive one datagram of UDP data, you can already start decrypting that and interpreting that. So you no longer have this problem where you had the TLS records that were incomplete and you couldn't start yet. It runs over UDP, which is interesting because a lot of corporate firewalls don't have their UDP open. So for most of us, that might mean that you cannot actually do it yet. And it also has one annoying feature, is UDP doesn't have congestion control. So it's often used for DDoS attacks. People just start sending a bunch of stuff to your server, and if your server starts interpreting that, it might break down, right? So there's a little bit of security that comes with that. It needs to be built into web servers, and that's also, I think, part of the reason why a lot of the web servers still say experimental is because they don't want this DDoS vulnerability. They want good congestion control. And the support, it is limited both in libraries and in web servers. I think the web servers do share some packages underneath where they can just pick a quick system package and implement it themselves, because some of them seem to use similar implementations. But it is still hard to use HTTP3 right now. All right, what does this mean for reactive streaming? Well, reactive streaming we've seen in quite a few places. We've seen it in WebSockets. We've seen it in things like Apache Kafka, reactive database drivers, all that sort of stuff. What this means is that we have an extra avenue over HTTP now where we could do reactive streaming because we no longer suffer from this head-of-line blocking problem that we used to have. The reactive manifesto came out in 2013. It basically says your application should be responsive, message-driven, resilient, and elastic, which means it should scale up and down, it should deal well with failures, and it should do something when I click a button, right? And most of the way Java world implemented that, I would say, is inside of a non-blocking kind of framework where we have an event loop that tries to handle incoming events, and it tries to be non-blocking all the way, right? That's how we tried to be reactive in the past. I'm going to show you with Spring WebFlux, and it's one of the implementations we have in Java. We have the Java 9 types of flows, publishers, subscribers, that sort of stuff. We have Vertex. We also have Spring WebFlux. I chose Spring WebFlux for this because I built it in that, and you're going to see it in the demo. Spring WebFlux has a couple of funnily named types. A mono is basically an expectation that you will receive either 0 or 1 of something. You can see here, this is a typical database transaction. So I'm running a reactive driver here, and you can just have a reactive CRUD repository. So all of this looks a lot like you would do in non-reactive land, right? It looks very similar. You just find something by an ID, and you expect to either find something or find nothing, right? And this is just your controller logic. Then it has a flux, which is basically I expect 0 or more elements, and it could be up to infinity even. Similar to our normal database logic, right? We can do a find all, and we expect to find, well, if you have an empty collection, you find nothing, and otherwise you find multiple elements. All looks relatively straightforward still, but these are the CRUD repository examples, obviously. So when you go to combining, it gets a little bit more complicated because you have to do everything in a non-blocking way. So what you're saying here is it's a bit of a silly example, but I thought, let's say you have an account with a name, and you want to find out whether that name is statistically more likely to have a lot of value, right? So you look at the database for this account, and then you flat map it, which basically means you're expecting that this one result will turn into 0 or more results in the end, with the find accounts by name, and then you map it to account get value. And this looks, for people that don't do reactive programming, it might take some explaining and some getting used to. It's a sort of stream processing where you're defining what is going to happen when one element enters at the beginning all the way to the end without ever actually doing the operations on the object. And the funny thing is that if you don't subscribe to this call, which we're doing by returning it as a get mapping, but if you don't subscribe to this call, this will also do nothing. It just sets up a sort of pipeline where elements start flowing through and start doing things in your system. And you can see already that, well, I'm combining one that turns into multiple. And when you think about what the possible error scenarios are in this case, which is super simple, you're already a bit like, I'm not really sure I've handled all the edge cases here, right? I've handled none of them here. But this gets more and more complicated the more you combine and reuse these things. And when you want to do 3 things at the same time, but then combine them back to one, and then do one that comes after that, right? You can imagine that the failure cases get a lot more complicated. All right, then you have one more concept I would like to show you, which is sinks. And you can think of a sink as an entry point to a flux. So you can think of it like a sink in the kitchen, where you throw something in and then it flows down, right? So you have this reactive pipeline you've set up, and then you have a sink somewhere. This one is a sink that publishes to many subscribers. And then you can call emit next, and then you can view the sink as a flux and share it among your friends. And what that does is basically everybody gets the end of this pipeline. And then when somebody throws something in the sink, it flows all the way down to the end, which can be multiple subscribers in this way. It's a sort of multicast way of dealing with elements. And it's very nice for combining fluxes in a way where you don't know what you're going to subscribe to yet, but all these things could be emitting things in the same sink. So in the end, it has one view, but you're going to dynamically combine these into one, sort of. All right, everybody still awake? Because this is... All right. One nice thing to mention is Spring Web Clients, ever since Spring 5, is by default reactive right now. You can call .block at the end, and then it will no longer be reactive. It will do a blocking call. But by default, the Spring Web Client is your first intro to reactive programming, because, yeah, it's now all reactive. Then one more trick I would like to show you is it's called server-sent events. And it's a way to do streaming over HTTP. And it was originally sort of feature, sort of bug. We used to have these images that loaded very slowly, right? You would send one image, and we would do that in something called chunked encoding. So you would send chunks at a time, and then in the end, you would have the full image, and it would display. And people might remember that from the 90s when you would load a picture, and it would load like this on your screen, right? So you would have an open connection, and it keeps sending frames, right? We've been reusing that, so that same open connection, it's basically you do a request, and you get the response, but you don't close the stream. And this allows the server to keep sending events. And these events can be whatever. Previously, we used it for large file transfers, but we can also use it just to send text event streams. So in here, I'm saying that I want to listen to this sync, which is interesting because the sync doesn't currently have any items going into it, but it basically means that I'm getting an HTTP subscription for whenever someone throws something in the sync, I'm going to get it out the other end over my HTTP connection. So it allows me to do some sort of dynamic readjustment of these fluxes into my sink, and then finally back out to the consumer, which is hopefully you. So what we've seen, mono, 0 or 1 element that we expect. We've seen a flux, 0 or many elements. We've seen a sink. We can throw something into it, and it's the start of a flux. And then we've seen event streams. I think it's about time for a demo. We really have to, because this demo requires the internet, and you are all going to connect to one of these sinks. And these sinks, this keyboard is connected to my laptop and then connected to the server via WebSocket. And then when I press a key on this keyboard, the sink is going to emit that event to your cell phones. And that's basically how the start is going to work. So you're going to subscribe to my event stream. And the idea was, I wanted a realistic demo for reactive streams, right? And you don't really need reactive streams unless you need to be really responsive or have lots of subscribers having lots of updates all the time. So maybe sensor data or something like that, right? But here with music, if you guys are too slow, it's going to sound awful, right? So, and also this runs on my server that fits in the palm of my hand on my home internet connection that has 6 Mbit upload. So there's a lot of challenges here, and we're going to see if it works. In the section on the right, I will explain that in a little bit. What you can already do is you can go to my website, and then you should see a screen that I will open in a second. And you can enter your row and seat number. It complains if somebody already filled in the same seat number as you. So then just pick a different seat number, and you'll be fine, right? And meanwhile, I'm going to hook up the keyboard. And if possible, your network should be on 4G or 5G, just to see if we can get as many people as possible. I know the internet is spotty today, but we might get at least a third of the crowd would be nice, right? All right, so you should be getting this screen, and then you can enter your details. I'm going to go for row 0 for now. And then you can enter the room name, which is JFAL. Doesn't matter if you use capitals or small letters. And then you should be getting... Ooh. You should be getting this screen with your number displayed up over there. And then because I just connected the keyboard, I need to actually connect the keyboard to the sync for now. Is everybody in? Still people? There's a lot of people in the back section. Holy crap. Well, it's going to mean that the brass section will do good. So for now, we're only going to play piano, but we're going to continue the demo and make it a little bit more exciting in a second. If it works. Big if there. It will, if your event stream gets disconnected, it will automatically try and reconnect the event stream, so I hope that you don't get too lost. All right. I hope my keyboard will connect now, because I actually need to have internet as well for this to work. And I'm actually getting an internal server error. Great. No, I can't blame the Wi-Fi. That's I'm going to try a little bit different then. We're going to try maybe not through the keyboard, but I'm going to connect the sync to something else, and we're going to see if that works through my cell phone, because my laptop is not really helpful right now. It works, yeah. So what you're hearing right now is there's 15 instruments inside this MIDI file. My server loads the MIDI file and determines whether a note should be sent to someone. And depending on which section you're in, it will send the notes for that instrument to your section. And each of the instruments is an individual stream over HTTP3. So you might be playing 5 instruments at the same time, which are all receiving notes from my server over a 6 Mbit upload connection right now, which is pretty cool, right? We wouldn't have been able to do this without the Reactive Streams technology, without HTTP3. I'm wondering if I... Yeah. It's... The only thing about HTTP3 is that I wish everyone had access to it. That's right now, that's my main problem. One of the large challenges for this project was finding audio recordings for each individual note for each instrument. You might notice that the violin sounds a bit like someone is stepping on one of those rubber ducks. I'm terribly sorry for that. What's interesting is that you are each connected. Hey, you're each connected individually to my stream, right? But the events arrive on each of your phones, like close enough together that it actually sounds like music. So there's 50 cell phones in this room who have a total of like 5 connections each to my server, so 250 connections, and they go pretty smoothly, apart from the internet problems here, sadly. All right. I'm glad we could do that part of the demos. I normally can also play the keyboard, and it sends to your phones, but sadly my Wi-Fi isn't working. But I'm glad we had at least part of the demo. How does this work? Well, I have an Intel NUC. I don't know if you guys know that. It's a little computing device. It's inside my utility closet at home, and it runs Kubernetes, which has traffic proxy at the front end. And then it actually deals with the HTTP3 traffic, and behind it, it's regular HTTP, which is not really a problem because the services are next to each other, right? They don't really need to go over the network. So traffic has this, it deals with my certificates as well, automatically, kind of nice. And then all your phones are connected over HTTPS. The keyboard was supposed to be connected over WebSockets, but sadly it wasn't. And then we use an Angular front end, which basically loads the music notes to your phone, depending on which section you're in. And the Spring Boot backend has a sync, which you subscribe to, and then it just keeps sending out notes whenever you need to play a note. Inside the Angular or the Spring Boot application, it looks a little bit like this. I have either the WebSocket set up to stream into the sync, or the MIDI file decoder, which decodes this file, and then basically it's an event loop that plays every 15 milliseconds. It checks whether it needs to send notes, and then it sends it to one of the syncs. I have a sync for every instrument that each of you are assigned to, and then through the subscribe to an instrument, you guys are subscribed to a text event stream that sends shorts, which get translated into like A3 or a B3 or something like that. So we've seen a little bit of history. HTTP 1.1, HTTP 2, the problems with head-of-line blocking they had, the problems with TLS encoding they had. Then we've seen how HTTP 3 attempts to solve these problems. An interesting part about that as well is because it's no longer solved on the protocol layer, which is primarily dealt with by OS-level engineers. So like you need to upgrade your Ubuntu to get a new version of TCP, right? Now it's inside the web servers, because UDP doesn't care about anything, it just sends. And then inside the web servers, you now have code to deal with congestion control, to deal with encryption, decryption. It's also why this feature takes so long to develop, because these web server engineers now suddenly have a much broader part of the pie, right? But it will allow more open source software and more people to help build this protocol to the next level, right? You could even do a custom congestion control window for inside your own cluster because you know you have a certain gigabit connection or something like that, right? We've seen how that interacts with reactive streams and specifically text event streams. And then, yeah, I was wondering, are there any questions? Yeah.
I was just wondering if you know Project Loom and if that will replace the reactive streams part.
Yeah, so that's an interesting question. So one of the very difficult parts, and I've tried to showcase that in the reactive part with even a simple feature yet, is that the reactive streaming paradigm has a very high entry bar. It has a very steep learning curve. So your engineers, before you start this, they will need to learn a lot about the way errors get handled and the way you can buffer and all that sort of stuff. And it's also not an imperative coding style, so it reads kind of difficult. You have to read these things in sequence and keep in your mind what type it is at what time. Project Loom and also Kotlin coroutines do an effort to get back this readability. And I'm very happy about that. And I think it will make a big improvement. And it might make it much more accessible than it is right now. Yes.
Okay. Nice. I guess only that trick where you do the server send event that will get lost maybe.
It could be. I'm not too sure about how the basically web servers will respond to Project Loom, but maybe we will see some sort of Loom controller, right? And we can do the same thing maybe in the future, right? Yep. Oh, sorry. No, go ahead, go ahead.
So what do you use for the playback? Web audio API or HTML5 audio? Or
I used the web audio API, yes. Oh, yeah, this is a fun one. So it's actually individually recorded notes. So every note is a separate audio file that gets rendered. There's a very difficult problem where if you cut off an audio file in the middle, a human ear will hear a pop. Because it sends a key down and a key up in the MIDI signal. So it sends when you should press and then when you should release. So it starts playing there, and at some point it needs to stop playing. So the way that's fixed is you have a gain node, and you can actually temper it back to like over a period of 0.25 seconds, which also happens in the real world if you stop playing, right? It's not like the sound is immediately gone. So it tempers it down back to like 0.01, and then you don't hear that. It's like a very strange popping noise made by the human ear if you suddenly stop a sound. But it was not trivial to get the sound to sound right, and still the violin sounded like a duck. So it's. Did you have a question also? Yeah.
Your application is running HTTP3 and the traffic is running same, right? So
It depends what you mean by my application. The Spring application is running on HTTP just regular, not 3. Traffic is actually doing proxying. So inside my cluster, it's all HTTP, and traffic does proxying from 3 to 1 in the background, 1.1. Yeah. Yeah. So it's a netty reactor, which is the web server that runs under it, and it has an event loop, and it dispatches. Or it's one thread that deals with every HTTP request. It's not synchronous. Yeah, exactly. Yes. Each phone has 5 different connections, one for each instrument that it was playing. And it's subscribed to the same sync. So this sync is a multicast sync. It can cast to multiple fluxes at the same time.
So if there are 100 phones, your Spring application has to handle 100 connections.
Yep. Yeah, over 6 Mbit upload. Crazy, right? Really cool. Yeah. Yes.
Why did you choose to use a WebSocket for the keyboard while using all this cool HTTP3 streaming for the audio part?
Because server-sent events go from the server to the client, and I didn't want to host anything here that... So you could connect to an upstream host that also does this reactive streaming kind of thing and stream through. But because I'm a client connecting to a host, the HTTP protocol is still you request and respond, right? So I could send just HTTP requests. That would work probably as well, because it's very fast. It's just tiny text messages. But if you want bidirectional traffic, so a lot of traffic going from the client to the host and the other way around, you should still probably use WebSockets, where if you have unidirectional updates, so the server might be listening to some sort of Kafka topic for updates, and the UI needs to reflect the fact that state has changed, then these text events are a very good way of doing that, because you don't have the client responding back a lot of the time. So it's still a bit unidirectional. That's kind of the reason. Yep. It is not now. It is also definitely not production code. So I would not use this as an example for your production code. For instance, these syncs that you're all subscribed to, I currently don't dispose them. I dispose them by throwing them away with my Kubernetes service and restarting it. Because it's kind of hard to deal with the problem that a client leaves, and they don't tell you they leave. But there are tricks for that. You can heartbeat them, and you can check whether they're still receiving messages. I'm thinking about putting it on GitHub, and I think if you tweet at me, I'll probably link it to you sometime. But I'm a bit embarrassed about what's in there. So, all right. Well, I think that was everyone. Thank you for your attention, and please rate in the JFall app.